Hey students, hopefully you guys are doing well. Here we are in week 7, and in week 7 we're going to be talking about structures, geological structures. Last week we talked about, we finished up plate tectonics a little bit, and we're going to be talking about plate tectonics throughout the rest of this unit, really, but different parts or different segments of it. And so we started off with plate tectonics, and we talked about metamorphic rocks and how metamorphic rocks actually play a role in tectonics and finish up kind of the rock cycle related to that. Now we're going to talk a little bit about how rocks actually behave under stress and strain, are related often to tectonics, and so that's going to be our focus today. So now if you look at this picture here, a little Land Rover down here for scale. This is a large mountain belt, right? Here behind you, a pretty large mountain, but this is just a dramatic kind of feature here. And you'll notice these rocks are bent. Now, rocks aren't naturally bent that way. You guys should hopefully know that when sedimentary rocks are deposited, it's deposited often by a fluid, and that fluid is these nice horizontal layers, right? And that's normal. But to have something like this happen, where you have this this bend in the actual feature, tells us that the rocks have undergone stress or pressure as they get pushed together, right? And often because of plate tectonic forces. So that's what we're going to kind of be focusing on today, is how those forces impact rocks. And in reality, the stress and strain impacts anything. So that's what we're going to be focusing on first, is this concept of what stress and strain is. Now, all of you have probably at some point in your life felt stress, right? And most people think of stress as some kind of a pressure put on you. Now, it could be academic stress, where you're trying to exceed something, trying to get that A, or trying to get something like that, so you feel a lot of stress on you or pressure on you to get something done. Or it could be an actual physical stress, where, for example, when I am moving my hand, right, I am actually putting a force or stressing my muscles. So my muscles move in relationship to that stress, okay? And so stress is the force applied, whereas strain is actually what changes because of that stress, okay? So, for example, in my hand again, it's good enough. I'll use this. I use this example a lot in class. When I change the stress in my hand, my muscles down here contract and expand, right? Okay. So what's happening here is these muscles are due to the stress are straining. Now, strain means the movement, the actual damage, or the resultant change in a material that can be measured. Another good example of this is in a ball, just a basketball or a tennis ball. I had one around here in my office a while back, and I can't find it. So I'm going to use the best that I have, which is I have in front of me here this ball of silly putty. Now, some of you guys might remember silly putty. It's just basically this putty that sometimes can act like a fluid, sometimes can act like a solid, right? So with this one here, if I actually push on it, it will change, right? So in that putty, I'm going to apply stress, and when I apply stress, it was once a sphere, and now it's been strained to form this kind of more planar feature, right? And then I can stress it and do whatever I need to. As I apply more stress, it gets more strained. So strain is the example of that. Now, in the relationship that some of you guys might think about in a muscle strain, when you apply so much stress to muscle, okay, I'm applying stress to my muscles right now as I move my muscles, but if I actually apply too much stress to it, we often might call that a strain. Okay, that's a medical term, and that's when you've pulled it or too far, where it's actually done some damage. Okay, so it's gone past what we call its elastic limit. It won't bounce back anymore because you've stretched it too far. Okay, so that's usually often called a muscle strain. Now, a muscle tear would be to the point where you've actually stressed it so much where you've actually damaged it permanently and tore it apart, right? That's the same kind of example if you have a rock or something like this. Here where I have my silly putty, I apply stress to it, it changes its shape, okay? If I apply too much stress to it, it can actually break apart, right? So if I have my silly putty here, and this time I'm going to, instead of pushing on it, I'm going to actually pull on it, which is a type of what we call tensional stress. As I pull on it, it gets thinner, thinner, and thinner until it breaks, right? Okay? So now I have both sides and they broke apart. And so that damage there, or that change in strain, is caused the material itself to break apart because it had too much stress applied for that object. Now, of course, every object has a different stress and strain relationship. My muscle has a different stress and strain relationship than the silly putty does, and different than this rock does, right? Okay, they all have different stress and strain relationships. Some of them are more rigid, whereas others are more fluid or more what we call ductile. So stress, in an earth science perspective, is the force applied, okay, or the pressure applied to the rock, okay, or to the material. And so this applies to everything, my ball, my silly putty, everything like that. There's a stress that's been applied, and it would change its shape, okay. Now rocks, you think of as being rigid. Well, they can be rigid, very rigid, and they can undergo what we call brittle deformation if that happens, but they also can be ductile or bend under certain circumstances. Okay, so if you apply pressure to this rock, it will slowly bend a little bit, okay, until it gets to what we call, and then it will bounce back elastically if you don't push it too hard. Okay, here's an example. Here's a ruler that I have here. Right. Now I'm going to apply stress to it. I apply stress to it, and it bends. So the stress that I'm applying here is causing it to strain or bend. Now if I release the stress, it bounces back to its normal point, right? Now normally rocks can usually only can take a small amount of strain, elastic strain, usually only 1 to 2%. So not much. Often we can't even see it in the naked eye lots of times. But stretching or thinning beyond 1 or 2 can cause permanent damage. Okay, under the right conditions can actually fracture. So let's talk about this a little bit more. This graph actually really helps us understand this. So as I apply stress, this material, this metal ruler, actually bends or strains, right? So as I apply stress, strain's applied. Okay, until it gets to some point. Now, if I've applied so much stress, it's going to come to the point where this metal ruler here permanently bends. And when I let go, it's going to still be bent. I don't want to do that because I don't want to ruin this ruler. But if I did, it would be permanently bent, right? Okay, so I mean, you can do this in a piece of paper in a sense. Here is this. If I bend it right now, it's going to elastically go back. Okay, so it's still within what we call its elastic deformation. But if I keep pushing too hard to the point where it actually there's a crease in it, now I have something that's gone past its elastic limit. It's not bouncing back to the way it was before, and it's what we call ductile deformation. Okay. Now, if I actually apply way too much stress to this, it can rip and fracture apart, right? Okay. And so those are examples of elastic deformation. The elastic limit, where it no longer can actually bounce back to its original position, and then what we call it the fracture point, which is where if you keep pushing pressure on it, it's going to break. Okay, all rocks exhibit this. All materials exhibit this. Your bones exhibit this. They bend a little bit, but if you push them on them too hard, they're going to break. Okay, and some materials are more rigid than others. And just like my silly putty here is not very rigid at all, so therefore it can bend quite easily. Whereas my marker here is a marker. I push on it, and as I try to bend it, it's barely moving. Okay, so it's much more rigid. It's going to go to its fracture point much faster than the silly putty will be. That bends really easily. So the type of material that something is made up of and the way it bonds together has a big impact on its elastic limit and its fracture point. Now, why is this all important in regards to rocks? Well, rocks behave the same way. They have what we call brittle deformation. And when you have brittle deformation, these rocks will break apart. Okay? So brittle deformation is an example of this. This is the process in which a material cracks, fractures, causing joints or faults in rocks. And we'll talk about what each of those things are, joints and faults, a little bit later. But let's say here's my a plate, and I drop it on the ground, and it will crack into many pieces, forming all these different cracks within the rock. So if I got this rock right here, and I get my hammer here, my rock hammer, and I start hitting the thing, which I don't want to because I don't want to destroy the sample, it will actually start breaking, right? It will go past its fracture point to do what we call brittle deformation. Whereas if I have my silly putty, which I have right here, okay, and then I hit it, then I get my hammer out and then hit it. Oh, there goes my silly putty. It has its elastic rebound, right? So it's elastic limit. I hit it so hard it barely made a dent in it. But there is a little bit of a dent, so you can see, I'll push on it a little bit, okay? As I go into it, it's actually been deformed, right? Okay? That deformation is our plastic deformation, okay? The process in which objects change shape without physically breaking or creating folds in rocks. Okay, now I'm going to laugh at myself when I watch this again and see that rebounding back. But anyways, so it's when the material itself will start to change. Like this dough here, or my silly putty, and I put that book on it or something like that, is going to squeeze it out into this different pieces. Well, rocks can do that too under certain conditions, and these pebbles that used to be like our metamorphic rocks, and when they're metamorphosed, used to be round, and they can be stretched out as you apply pressure to it, right? So that's your plastic deformation. So there's different types of deformation when you have your rock deformation. You can have what we call an undeformed rock, where we just have the weight of the rocks on top of it. They're usually these nice flat-lying beds like this. Or as you push a lot of stress on it, you can change the rock to become a metamorphic rock. And you can get folds in the rock like this right here. Okay, so here my silly putty again. Okay, I'm first of all pulling it apart, so that's a type of stress. We call it tensional stress, where we extend it out. But if we push it together, notice it's going to actually bend and fold. Okay, so that's a compressive stress. Okay, and then compressive strain that goes along with it. Now, so these are when we have this happen in rocks, they usually happen under different conditions. So if I get this silly putty, and if I heat it up, this is going to flow better, right? Okay, just like ice in a sense. If when it's ice in the solid state, it's going to break more and act more brittly. Whereas if water is in its liquid state, it's going to be able to flow quite easily, right? It's the same thing with any material. Under different conditions will cause something to change in different ways when stress is applied. So if I push on this, okay, very slowly, it has a plastic deformation to it, right? Okay, so no, I can't do this very well here, but I got this on here, and if I pull it really fast, it breaks more. And it still has some plastic deformation, but then ultimately it bursts, right? The faster I do that, but if I do that slowly, that same piece, and do it slowly, it's not going to break until well out, keep going, finally broke. Okay? So, but if I got that same material and then do it fast, let's see if I can do this fast, it breaks breaks brittly. Okay? So, there's different factors that impact this. So, if I do a slow strain rate, okay, or time, the silly putty will break either brittly. So if we do it fast, sorry, it will break brittly. If we do it slow, it will actually break ductily, okay, based on how much stress is applied per unit. Also, if temperature might have a difference. If I've got this silly putty and put it in liquid nitrogen and then dropped it on the floor, it would fracture in a lot of pieces. However, if I got the same silly putty and then heated it up, it would flow even better.